Good evening, everyone. My name is Renu Raman Sahu, and I will be doing the TSC for this course, Physics of Materials, every Friday from 7 p.m. to 9 p.m. Am I audible? Okay. So we will be discussing the assignments of the previous year. So this will help you to solve the assignments which will be coming this year or the current assignments. So we'll get started. But before that, do you have any questions or doubts in the lectures that you saw this week? Okay. I will just go through briefly what was there in the previous class. So uh, we'll just have a very brief discussion. So what was there? So the first lecture was mostly about the introduction of the course, and then what it was discussed was the second lecture was about the properties of materials. So here the professor asked the question, what is a metal? So we don't think of a formal definition of a metal. So it is difficult to formally define what exactly is a metal. So what we actually do is to look for the properties of the material. So once we are given a material, we know the formal definitions of certain properties which we can measure. We measure those properties and compare with the existing properties of the other known materials. And then for a certain range of the values of these properties, we can categorize this material. For example, certain material will have a particular range of conductivity, let's say. So we will categorize them as a metal. So metal have certain range of properties about electrical conductivity, thermal conductivity, and so on. So this is how we will look into the properties and compare it with the existing properties, and then we go for the categorization. So what are the properties? Uh, so there are certain properties. So we can classify these properties as mechanical properties, chemical properties, electrical property, thermal property, magnetic and optical. Understanding these properties is important, uh, like from the engineering perspective, because if we know the property of certain material, then we can design a device with respect to certain specifications. The mechanical properties include these many properties like the modulus of elasticity, the yield strength, tensile strength, ductility, resilience, toughness, and hardness. And there are chemical properties which can be defined by these many properties: bonding energy, ionization energy, electron affinity, and deuterative properties. Uh, so in the lectures, the professor has like described this nicely. Then we have other properties. For example, in electrical properties, the properties are like conductivity, dielectric constant, the band structure, electron mobility, and so on. The optical properties will include the refractive index, absorptivity, reflectivity, and transmittivity. And the thermal properties will have the thermal expansion, conductivity, and specific heat. And the magnetic properties are like the what is the Curie temperature of the material, the reminiscence, coercivity, the soft magnetic materials, and what are the hard magnetic materials. So all these properties, we have a very formal definition, and we know precisely how to get the values for these properties, the numerical values, or in other words, we can quantify them. So, the purpose of this course is to understand from certain models or from understanding of some the basic properties in terms of atoms and their bonding, how these properties will come into picture, and what is the relation between these properties. For example, metals will have uh, like usually high conductivity in high electrical conductivity uh, will have the materials with high electrical conductivity will have high thermal conductivity as well. So that is just one such correlation. There can be correlation between the other properties as well, which we'll see in later classes. As an example of a model, thermal expansion was discussed. So here is an example of a bimetallic strip. If at temperature T naught, A and B are two metals, and if A expands more than B at some higher temperature T1, then it can be bent if we apply some heat to it. So, so this is actually expanding, and the rate of expansion is different for these two materials. There are some other materials which actually shrink when you apply the heat. Those kind of materials are called heat shrink. And to define what is how good a material is at expanding when heat is applied to it, there is this property called uh, coefficient of thermal expansion. So it is defined this way: if L naught is the temperature, L naught is the length of the material at temperature T naught, and LT is the temperature length of the material at temperature TE, then this is how you can define alpha. Okay. So now to understand, this is at the macroscopic level. What is happening at a microscopic level? So to understand that, uh, the example that was given was that of an ionic crystal. So suppose we have NaCl. So this is uh, the salt that we use in the food. So how these crystals form? First, Na plus ion will form, and you need to give an external energy to the system of around 5.1 electron volt, and you have to have the chloride ions, and to have that, you need to give an electron to it. And when electron comes to this chlorine, the energy that will be released is 3.7 electron volt. So this is the energy released, and this is the energy absorbed. So the total change of energy is 1.4 electron volt. So this is the energy that we have to give externally. That means the energy of the system has increased. So now, if we need to have NaCl, the overall energy of the system has to decrease. So that is accounted for by the Coulombic attraction between the sodium ion and the chloride ions. So it is just the Coulombic attraction here. And if we look into how they interact, uh, s- uh, then we have to look for uh, another force as well. If the sodium atom and the chlorine atom, they will come so close together, then their electron clouds will overlap, and this will not happen. Why this will not happen? Because one, due to the Pauli exclusion principle, like the same energy level cannot be occupied by more than two electrons. So that's where the repulsion comes in, and there would be Coulombic repulsion between the electron cloud of both the atoms. So that thing can be accounted by this term, where E is B by R to the power 10. So the total energy of the system, when all these energies are taken into account, are, this is the Coulombic term, This is the electron overlapping repulsion, and this is ionization and electron affinity. Now, if you plot this as a function of R, the type of graph that you get is this. Now, the question that we were examining was, why do a material will expand when the heat is provided? So, we try to understand this plot. So, when the temperature is very low, there is no thermal excitation, and the average energy will be this, because the system will try to come to the lowest energy as possible. So, this will be the mean radius at temperature T naught C. When we increase the temperature to T1, then it will oscillate, it can oscillate between this range. And here you see the mean of uh, the mean radius or the mean distance between the atoms, that is somewhere towards the right side of the previous point. What it means is that this R is more than this particular R. So again, if you increase the temperature, then the mean shifts towards the larger distances. So it is actually the asymmetry of this potential between sodium and the chlorine ion, which is responsible for the expansion of the solid. So had it been a symmetric one, then these points would not have shifted, and uh, there would be no thermal expansion. So this is the example of a model how from a microscopic interaction we can explain the thermal expansion. Okay, this was all. Now we'll go to the question answer. So I would like you to participate in the discussion. So answer if the following statements are true or false. It is important to understand the exact thermal profile of a flame in order to use it for cooking. I mean, is it true or not? Say, suppose someone wants to cook. Does that person necessarily know? I mean, there are a lot of chefs, right? Do they know what is the thermal profile of the flame? So you know what this thermal profile is. So if there is a flame here, it is just the mapping of the temperature. It's here the temperature is like 3000 Kelvin. Then at the outer layer it is 2000 Kelvin. So it is basically at different point. What is the temperature? Does a person who is a chef has to know this in order to cook? Yeah. What is your opinion? I mean, you don't have to know, right? All you care about is the what how the food is like if the food is getting cooked or not. So it is what? Yeah, exactly. So it is not important. So this statement is false. Okay. So now the next one. A model is useful if it can predict data over a full range of experimental conditions. Is it true or not? Like, what do you think? Yeah, exactly. So this is false. Uh, Empirical models are useful even if the underlying science is not understood. What about this? See, it is an empirical model. What it means is the model can replicate the behavior up to a certain condition. Uh, like you're getting, for example, thermodynamics was there even before statistical mechanics was there. You're getting it right. Like uh, so how for example, how do I say the gas law, like the pressure is in, uh, say the thing, what is the underlying science is not always understood correctly. uh, like before, even before the kinetic theory was there was this Boyle's law and Charles law. All these things were there, the gas law, but it was not known. So even the existence of atom was not known before. So the underlying science was not known, but there were models which were quite successful. Because why? Because these empirical models are like mathematical relations and the actual measurements which has been repeated uh, quite a number of times in the lab. And uh, the only thing is they work out correctly. So as long as you have a model and you don't exactly understand why, what is the underlying science, then also these empirical models are useful. Like, are you getting this point? Yeah, exactly. Yeah. So these are like mathematical relations between let's say two physical variables. So and it is the work of uh, uh, so for example, earlier we knew how the heat capacity will change with respect to temperature. But until the advent of quantum mechanics, it was not correctly understood. For example, the Dulong-Petit's law. Eh, People knew that what would be the heat capacity of solids at high temperature, but why it was so, it was not understood. So I hope you're convinced that this is true. Yeah. So now the next statement: there are no instances where theoretical prediction has been made even before the experiment has been conducted. Yeah, true. Okay, so what about the last one? For all materials, as temperature increases, electrical resistance increases. Yeah, true. So there are materials in which the electrical resistance actually decreases. Okay, now we go to the next set of questions. Okay, so the two ends A and B of a long metal bar are kept at two different temperatures, 60 and 100 degrees Celsius. and a four probe measurements shows. Okay, so what does a four probe measurement will do? What does it measure? Any idea? Sorry. Y- Yeah, exactly. So in a four probe setup, what we do is there are four probes. There are four probes like this, and we like put it on the material, and we inject current. We inject current on two of these probes and measure voltage between the other two. So and thereby we get the conductivity. Now it is now look at the thing that it is a long metal bar. So so a metal will consist of the ionic cores and the free electrons roaming around in it. So now you can think what is contributing to the conductivity of the material, conductivity of the metal. So this is a transport of like you can uh, uh, is it the ions or the electrons? Yeah. So electrons are mobile in it, and majority of like almost all the contribution to the conductivity comes from these electrons, and from the ions. So ions are actually the static core which make up this metal, and the contribution from those ions will be really very less. Like you're getting the picture why, right? Because yeah. So the conductivity due to these ions will be really less, and so what we have to think of is what will happen at two different temperatures. Yeah, exactly. So what will happen is that the electrical conductivity will change drastically at these two different points. Okay. So the electrical conductivity will be different at 2 points. And what about the ionic conductivity? It will be similar. Yeah, correct. Okay. Now we go to the next question. Okay, the three states of material are solid, liquid, and gas. Among the various properties of a material. Okay, now so we just discussed what are these mechanical properties, electrical properties, and thermal properties, right? These mechanical properties are, for example, like the Young's modulus. So we get these mechanical properties from this stress strain curve. And how do we measure that? So there would be this sample. So and then we pull it, and pull it. We measure the something called the stress strain curve. And on doing that, up to a certain point of time, it will be linear, and then it will be non-linear, and then it will break down. So most of the mechanical properties, those are determined from this curve. For example, the slope will tell you about the Young's modulus. This point will tell you about the tensile strength, the yield strength, and so on the other properties. So to measure the mechanical properties, okay, now can you tell me which of these statements is true? Yeah, solid can have mechanical properties because we can uh, cut a solid into this shape and do this experiment and measure this. Okay, can gas have mechanical properties? No, obviously because we cannot mold a gas into this and do any kind of this measurement. Okay, so the liquid served electrical. Yeah, but pressure we mostly consider in the thermodynamic properties because pressure is like it the motion of random motion of the molecules, uh, which actually is nothing but the uh, temperature. Yeah, yeah. Liquid can have electrical properties because what we need to measure is this conductivity and conductivity or the resistance. So this can be easily measured in a, like you can have a closed circuit. So we can measure the electrical properties. So liquid can have the electrical properties, and gas, as you said, yeah. So gas also can have the thermal properties. Okay, now we go to the next question. The resistance of a metal filament used in bulb goes up with temperature. Yeah. So what? Yeah, it is the electrical resistance actually. So it is called something called coefficient of. So just like you had this coefficient of thermal expansion, right? There is something called coefficient of resistivity. Yeah. So coefficient of resistivity usually for metal it is positive. Okay. And so what it means is that if your resistivity rho at certain temperature T is rho T, then it will be something like, okay. So this is called this coefficient of resistivity, and it is usually positive for most of the metals. Okay, so it will be true or false. Yeah, it will go up. So this statement is true. So usually in bulbs, uh, the metal filament they use is tungsten. Okay, and it has this coefficient of resistivity as 52.8 nano ohm meter, which is a positive quantity. Okay, so we'll go to the next question now. A bimetallic strip in an electric iron box works as a. Uh, can you answer this? Yeah, so it is a iron, electric iron. I mean, it can bimetallic strip can work as an indicator as well. But in iron, uh, like mostly they don't use a temperature. No, a bimetallic strip is this. Like you got it right. It is not a source. Yeah, there are mechanisms in which you can regulate the temperature as well. And is it? Yeah, so what it will happen is, so there would be a coil kind of thing, and on temperature, the, the curvature of this coil actually changes. Okay, I'm drawing it badly. So this will, the basic thing is that it is a bimetallic strip with different coefficient of thermal expansion. Yeah, and it can also, uh, you're saying something. It can also work as a switch. For example, at a certain temperature, let's say you have kept it like this, and A expands more than B on heating. So this is your zero condition. You apply heat to it. At a certain point of time, it will become straight, and then if you hit furthermore, it eventually its length will become more than that of B. So this is how it can be used as a switch as well. Yeah, so you can use it as a switch, and if you know the precise, if you know, if you know precisely what is the, if temperature is the only reason why the curvature of this is changing, and there are no other mechanical forces, if you are so sure about it, you can use it as an indicator as well. But it cannot be used as a heating element. Yeah, it is not a source. Okay. Uh, so it can be used as indicator because, uh, but since it is saying that it is an electric iron box, I have not seen an iron which is uh, which has a temperature indicator which have this bimetallic strip. Yeah. Okay. So which material property is responsible for the formation of ferric oxide in an iron pillar? Okay. So what is the see, what are the thermal properties? The thermal properties are mostly thermal expansion, thermal conductivity, and like we can have a quick revision. See, these are your thermal properties: the specific heat, thermal conductivity, and thermal expansion. And the chemical properties are this: the bonding energy, ionization energy, uh, electron affinity, yeah, and the deterioration. So now you say, think the thermal properties, any of these properties. So measuring any of these properties will not tell you why this ferric oxide has formed. So what is a ferric oxide? Yeah, it is this. So this will form if, yeah. So first you have to have this thing, uh, and it depends on what is the bonding energy, what is the electron affinity here. So you get it right. What is the properties that we need to consider? So electrical, then what we have to measure? We have to measure conductivity. What is the mobility of the material? So we don't usually care about these properties. What we need to know is that, Yeah, the conductivity gets decreased because there is an introduction of the other species. But at the first place, why the species is forming is because of different affinities of electrons to this iron and oxygen, or there are different binding energies. So the correct answer would be the chemical properties is responsible. Yeah. Okay. So the thermal expansion coefficient of an ionic material is impacted by its electrical conductivity. Is it true or false? This is ionic and this is electrical. Yeah, correct. Yeah. So the ionic material, it will not be affected by the electrical conductivity. These are two different species. The resistance, but resistance means sorry, your question again. Yeah. So what you were asking is the conductivity of the material. So resistance basically means the conductivity, right? Yeah. Yeah. So if it is mostly the electrons are contributing in that material, then it won't be affected. But if uh, the majority carrier are the ions, then it will be affected. Yeah. Okay. Now, this what is an example of a material with excellent thermal conductivity but poor electronic conductivity? Graphite is a very good conductor of heat as well as yeah. See, iron you should know, right? Because iron is used mostly in the cooking ware and all. Aluminium is very widely used in this cooking ware. So, uh, iron and aluminum, these are like known metals, and they have very good thermal conductivity as well as uh, the electrical conductivity. So this graphite and diamond, these are like the same element carbon. But what is this graphite is? Uh, Graphite will be this hexagonal sheets arranged in stacks, held onto each other with van der Waals forces. And if you look at one carbon, so it will be sp2 hybridization. Okay, this and this sp2 hybridization, and there will be one p orbital. See, uh, there will be s px py pz. So sp2 will be hybridized, and pz will be, suppose this is your plane of the carbon. So this is the plane. So there will be the p orbital will be coming perpendicular to this plane, and there the electron will be free, and those electrons can roam around in the seat, which is why the graphite is a very good conductor of electricity. And but in diamond it will be sp3 hybridized, and because of that all the electrons are tightly bound, and that is why there are no free electrons in diamond to conduct electricity. So diamond has a poor electronic conductivity, but it is a very very good uh, thermal conductor. Okay. So the example is this one. Okay. So materials with, you're saying something? Okay, okay, yeah, yeah. The materials with negative thermal expansion coefficient can be used for sealing. Yeah, it is a heat strength material. Perfect. So it, like if you have gone through the lecture, then there is an example the professor has told. Suppose we have two wire and you tie it with a heat shrink material, tie them both in with a heat shrink material like this, and you cover it up, then apply heat to it. Then what will happen? This will shrink and there will be a very tight bond between these wires. So this can be used for sealing the joint between the two wires. Yeah, it is kind of that. So it is that a professor has explained in the lecture. Okay. Now, the uh, what? Yeah, what do you think? Yeah, it's true. Yeah, because you can just like put the wire and then hit it, and it will contract and seal. Yeah. So what about this? A washer to seal again leaks in joints between tubes. Yeah, it cannot be used as a washer. Yeah. Okay. Yeah, true. Now the next question: the energy versus distance curve used to describe the thermal expansion in a material is a combination of which energy? Coulombic. Yeah. Yeah. Uh, we just discussed the formation of sodium chloride. Yeah. So how? So we need to form this Na plus, the Cl minus, and then we have to. Uh, so and we need to have an mechanism why it will attract towards each other, and then we need to have a mechanism why it should repel each other, so that the effective uh, potential looks like this. Okay. So how do you form this Na plus? This can be formed if you remove one electron from this. So this energy that you need to provide, that is called ionization energy. Electron affinity is, yeah. So if you give an electron to this chlorine, then the system will lower its energy and energy will be given out. So that energy is the electron affinity. Now once you have these two spaces, Na plus is a positively charged particle and Cl minus is negative. They will attract each other by a Coulomb attraction. Yeah. So this, if you plot, it will be like somewhat like this. And this ionization energy and electron affinity, so these are just the constants for this material. And if you sum both of them, for NaCl it turns out to be 1.4 electron volt. So which is 1.6 10 to the power minus 19 joule. So at infinite, if you just plot it like this will be 1.4 minus 19 joule. And there will be another interaction if they come too close to each other. So this will have an electron cloud surrounding it. This will have an electron cloud surrounding it. If they come too close, these electron clouds will overlap each other, and that is not allowed by the Pauli exclusion principle. And there will be Coulombic repulsion, and that can be modeled by this E is equal to V over R to the power 10, which will look like somewhat. It will look like this. It will fall like this. At R, when R will go to 0, it will increase like this. And if you sum all these three contributions, you get this solid potential. So what are the uh, contributions? The ionization energy, the electron affinity, and the electron cloud repulsion energy. So this is your correct answer. Okay, now this question. Yeah. So had it been symmetric, then what would have happened? Yeah, exactly. Remains unchanged because if it is like symmetry, okay, this. So if it had been symmetric, so at whatever temperature you were, let's say T naught, here you were, then the mean position is here. If increase the temperature, the mean is here. Further increase, the mean is here. So it will basically remain unchanged. And we saw that it is the asymmetric nature of this potential which is responsible for the thermal expansion. Okay, here the mean is changing. Yeah. So that is all for today. Thank you. If you have some other questions or any other doubt, you can let me know. Okay, sir. Yeah. Yeah, this will be weekly and I will be discussing about the previous year questions. So you can go through the material and these previous year questions will be your like practice questions so that you can this will help you to solve the what are the current questions. Okay. So I think we can end the session here. Thank you so much for joining. Yeah. Yeah, we'll try to have this interaction so that it doesn't become boring. Yeah. Thank you so much. Yeah, true. Yeah. So we'll keep the session interactive so that it will be like beneficial for like all of us. Okay. Thank you.